Okay, guys, here's what we're doing to wrap up the day, the unit, and the year. Now, guys, you understand that when we say that, that doesn't mean that you have learned everything that you're going to learn. This is your second pass at chemistry. Your first pass was general chemistry. Your second pass was AP chemistry. But where you're really going to learn this material is over the next 6 weeks as we review for the AP test. So guys, all that this means is that you're now done with try number 2. And then after that, we really get into this and you start learning stuff. So, guys, with that said, what we're going to do today is we're going to talk about something called the Nernst equation. Now, the problem is this. They took the Nernst equation off of the AP equation sheet, and they replaced it with a generic form of the equation that doesn't just apply to electrochemistry, but it applies to equations in general. So we're going to teach this as if the Nernst equation was still present on the AP sheet. And understand the Nernst equation is still valuable and you're going to enjoy the logic behind it. But then unfortunately what used to be the grand conclusion becomes, and oh by the way, look at this other equation that's kind of like the Nernst equation but it's more generic. Totally stealing the crescendo. But we're going to make it work. So guys, you ready? Here's what we're going to do. We are going to talk about now mathematically the very thing that we just described in homework conceptually. So here's what I'd like you to do, and I really want you to do this, largely because I know it's going to be on the test. So let me get my writing utensils. And guys, here's what you need to do. What I want you to do is I want you to draw yourself a battery. Make it fairly large, maybe about 1/3 of your sheet. And let's go back to what we know. Let's make it a copper zinc battery. And hey, why don't we make this familiar? So let's put zinc on the left. Okay? That way we're all talking about the same directions. And when I say direction, I mean travel of electrons. And guys, what I want you to do is I want you to label this with everything that you know. Just brain dump on the paper. Labeling the parts, drawing arrows to indicate directions. Maybe think about the salt bridge, what's in there, what direction things flow. Everything you got. Sulfate's good. You could mix things up and go with a nitrate or an acetate. No, I know. Just don't use phosphate because that does chemistry with water. But guys, and frighteningly, I'll bet one of you remembers the number. What voltage does this create? 1 point what? 1.10? I think it's one. Okay, so we can even put in the voltmeter. 1.10 volts. Again, that's just cathode minus anode with reduction potentials. I knew one of you would remember. So you know what? No sense in my waiting. I'll start drawing too. No, it's true. I can. Someday you are all going to look back, hopefully fondly, on your AP chemistry experience, and you're going to think, what did I learn in AP chemistry? And for some of you, the only answer will be what gruntled means.
Are there like short answers?
short answers? We'll talk on Monday. Please don't. Yeah, you're going to find that after those AP graders have been sitting in an unair-conditioned gymnasium, grading 100,000 AP chemistry exams, I've never been, but apparently there's a lot of heavy drinking in the evenings. Gil does that for stats. Yeah. Guys, understand that because those are the people that grade your AP tests, you don't want to be funny. You want to be appropriately. So guys, this is what I've got, and because I started after you, I'm assuming you're either there or beyond. What do you have that I don't? What did I miss, Rachel? So I kind of did that with the arrows. I went metal to ion and ion to metal. Good, yeah, so I'd like to do that. So I'll just put it here. So here, as the battery runs, the molarity is going up. Here, as the battery runs, the molarity is going down. Which then, guys, reminds me there's one other thing that we should, well, at least one other thing that I missed. I don't like the way I drew that. Let me do that a little differently. So let's do this. I know this seems the same, but think through this with me. So here, we have an increase in molarity, and here we have a decrease in molarity. Is that okay? Because there's another thing we need to talk about. The mass of the electrodes. I don't know how to abbreviate electrodes, so I'm just going to go with that. So guys, in the anode cell, the one that's on the left, and you guys understand this, right? The anode doesn't have to be on the left, so don't always count on that. How do you, well, we'll talk in a minute. Let's answer this question. So the anode's on the left. So guys, what is going to happen to the mass of that zinc electrode as this battery does its thing? It will decrease because atoms are going into solution. And then obviously the mass of the reduction electrode at the cathode will go up. So guys, anything else? Yeah. Yeah, you could include oxidizing and reducing agents, but relative to battery conversations, we don't really, yeah. Others? Okay, so guys, let me ask you a question. And maybe you circle this on your drawings, maybe you don't, up to you. But guys, understand one of the things that they're going to do to you on the AP test when you see a battery problem, doesn't always mean we will, but if there's a battery problem on the test, they love to sort of pick at your understandings by giving you different types of information that would lead you to understand which is the anode and which is the cathode. So guys, given all the things that we have labeled on the board, which of these bits of information are sufficient to tell you which is the anode and which is the cathode? Go ahead, give me one. Yeah, so one could be the direction of electron travel, because it always goes anode to cathode. Give me another one, Talmadge. Wow, yes, that would be hideous. I've never seen that on an AP question, but that would be nasty. Well, no, I mean, you'd figure it out, but they could give you the direction of travel for the ions in the salt bridge. I've never seen that as an upfront bit of information. Typically, it's a follow-up question that says, what direction do the ions travel in the salt bridge? But you're right, they could. Matt, give me... Yes, they could give you changes in molarity. That would definitely work. What else? Go ahead. They could give you changes in masses of the electrodes. And actually, they did that on the last one, which I think was 2013. What else could they give you? Yeah? Well, sort of, but what they could give you is this: zinc, copper, and the reduction potentials. You know, fundamentally, they won't do this anymore, but they used to do this all the time. They would just give us this chart, and they would say, you build a battery out of zinc and copper, given this, which is going to be which? So how do you know which is going to be which? So which is the bigger number going to be? The cathode, right? This is a reduction potential chart, and so whichever one of these, zinc or copper, has the higher reduction potential will be the thing that gets reduced, making it the cathode. Now understand, they could still do that on our test. They just wouldn't give us the data in a big table, but they could give you the reduction potentials just for zinc and copper, and then you would just compare the two, and whichever value is higher would be your cathode where reduction takes place. Do you get the idea? Okay. You guys good? Was that helpful? I don't care if it was helpful. That was helpful. You need to be able to do this and do this well. Yeah. Yeah, I've never seen that quite like that, though. What they could do is give you, they could give you the half reactions for that. They could give you something that, they could do that. They could go, as this reaction goes on, the half reactions are zinc becomes zinc ion plus 2 electrons, and copper 2 plus 2 electrons gives you copper metal. They could definitely do that. I've never seen it with arrows, but they could give you the half reactions. And then, of course, this is oxidation because electrons are a product. That's reduction because electrons are a reactant. They could certainly do that. You guys okay? Yeah. Please. It's the whole... No, it's the whole cell. So the anode is all that is contained in the cell where the oxidation takes place. Yeah, although that said, if in battery speak, we would then call this strip of metal the anode. The generic term is electrode, but the electrode where oxidation happens is the anode, and then they would refer to that strip of metal as the cathode, but technically it is the whole cell. Okay. Anything else, y'all? Good review for the test on Thursday? Okay, so what are we going to talk about today? Well, guys, what we're going to talk about today is this 1.10 volts. So guys, drink deeply of this idea or you're going to miss what we're up to today. So guys, we understand where that number comes from, right? Cathode minus anode, reduction potentials, cathode minus anode. The question is this: when does this battery, this zinc copper battery, when does this battery generate 1.10 volts? Well, it is at the beginning. But guys, what does beginning look like? And sadly, it's not defined on this table. We did talk about it when we talked about reduction potentials. But guys, let me answer the question without looking for it on a table. We did allude to it, but let's talk about it. Guys, this battery generates 1.10 volts at the beginning. I like the idea. But what is going on at the beginning? And you could write this into your diagram if you'd like. Here's what beginning looks like. This is a 1 molar solution. and this is a 1 molar solution. And it's at some standard temperature, which I think is 25 Celsius. I'm not exactly sure. But guys, this is at standard conditions, which is, I think, 25 Celsius, 1 atmosphere of pressure, which matters if one of these was a hydrogen cell, and 1 molar solutions. So when those 3 things are true, the temperature's right, the pressure's right, and the molarity's 1 molar, this battery creates 1.10 volts. But for how long does it do that? 1 instant. And guys, after that, after you build this battery, and you're going to see this in lab when we go next week, guys, after you hook up this battery and the minute you set it into action, that voltage drops linearly to death. So guys, let's talk about this idea of dropping to death. So guys, what is actually changing in the battery that causes the battery to die? The concentrations. See guys, this starts at 1 molar and this starts at 1 molar, but let's remind ourselves what we said and then tie this back to the homework question. Guys, what is going to happen to the molarity at the anode as the battery does its thing? It's going to go up. And what happens to the molarity over here as the battery does its thing? It's going to go down. Guys, this is question 8C. And D, because look at what's happening. As this battery does its battery thing, zinc is becoming zinc ion. But as the concentration of zinc ion goes up, it's harder for those atoms to enter solution, and that works against the battery doing its thing. Now guys, what happens over here in the cathode cell? Well guys, here reduction is taking place. And so we said in homework that the more copper ion we have, the better the battery works. But this battery, as it does its thing, is always consuming copper ion. And so as the copper ion concentration goes down, there's less copper to turn into a solid. And as a result, that also fights against the battery doing its thing. So guys, we basically have 8C and 8D lumped together, because this is going up, which fights against the battery working well, and this is going down. I know it's not exactly what it said in question 8, but this is going down, and that also fights against the battery doing its thing. And as those concentrations change, the voltage goes down because the battery is less able to do its battery thing. You get the idea? So guys, when then does the battery die? No, it won't go to 0. There's a magic word. Not necessarily equal, but it is an equal concept. When does the battery die? When it reaches equilibrium. But guys, the question is an equilibrium between what? And the equilibrium exists between the concentration gradient and the voltage potentials. And when those two offset each other, that is the point at which the battery dies. So we would say then that the battery dies when it reaches equilibrium. Does that make sense given everything we've talked about? Is that okay? Okay, so guys, let's do this then and pull that together into maybe a tighter nutshell. So guys, write down what of this you feel you need to, but this is a summary of everything that we've talked about. So here's where we are right now. To this point, we've studied batteries, and we've made these observations. First of all, they're spontaneous. Guys, how do we know they're spontaneous? They all have what kind of voltages? Positive voltages. And so what happens if we build a battery and we do cathode minus anode and the voltage is negative? Switch them. We identified them wrong. So guys, batteries are spontaneous. We know that because they have positive voltages. And guys, we have then now included this idea that they exist at standard conditions, which is 1 atmosphere of pressure, which is important if it's a hydrogen cell, and then 1 molar concentrations. And guys, from this then, we can calculate voltages. And this is great, but it doesn't actually reflect what happens to the battery as it does its thing. The reason is because the concentrations change. So guys, what happens to the concentrations in the cells as the battery does its thing? And it's not enough to say they go up or they go down. One goes up and the other goes down. So let's see if you can do this without a picture. Don't look at your picture. Which cell does the molarity go up, the anode or the cathode? Anode. Anode is oxidation. Oxidation is losing of electrons. The metal loses electrons and goes into solution. So then, of course, where does the molarity go down? And that's in the cathode where there's reduction. So guys, eventually then what happens? Well, eventually what happens is these batteries reach equilibrium. As reactant becomes product, they finally reach equilibrium, and at that point, the battery is dead and the voltage falls to 0. You get the idea? Does that work for you? Okay, so guys, here's what we now know. We now know that batteries die when they reach equilibrium, and when these things reach equilibrium, that is the point where the voltage becomes 0 and the battery is dead. Do you guys understand what we're doing conceptually? Because we're about to do it mathematically. You okay? Okay, so guys, let's do this then. Let's switch gears and let's get into this mathematically. So guys, understand that what we've said is dead batteries are all about equilibrium. And guys, when you think about equilibrium, what do you think about writing to describe equilibrium mathematically? Kc expressions, products divided by reactants. So guys, let's do it. This is the equation that allows us to figure out when batteries die. Write it down. So guys, this equation is the equation that allows us to figure out what the voltage of a battery will be as its concentration changes. Now guys, what I want to do is I want to define these variables for you, and then we're going to take this equation and we're going to cast it in a real life situation and see what this equation allows us to do. So guys, let's define our terms. You may find it easier to just draw little arrows and say, here's what these mean. So guys, E sub cell is the voltage of the cell at any conditions. It's the actual voltage. Now guys, what is E naught cell? Remember, naught's the degree symbol. What does naught always mean? Standard conditions. So guys, E naught cell is the voltage of the battery at standard conditions. Now guys, how do we come up with that value? Reduction potentials, cathode minus anode. So guys, we calculate this value given the standard reduction potentials, and that's just cathode minus anode. You okay with that? Now guys, this 0.0592, this is a bringing together of a bunch of different variables. It includes things about the universal gas constant, surprisingly enough, temperature, some other things. We're going to talk about that at the very end of the day today. Just remember, you can write down the number. So guys, what then does N represent? The number of moles of what? What do you suppose it's going to be given that we're talking about batteries? Electrons. Guys, this is the number of moles of electrons that are skipped around. And then, guys, we need to talk about Q. Do you remember Q? So Q is the same as what? Kc. But what's the difference between Q and Kc? So, exactly. So guys, Q is Kc at non-equilibrium conditions. We call this the reaction quotient. And guys, you may recall that the reaction quotient is the same as Kc, only it's not at equilibrium. So it's the product divided by reactant concentrations at non-equilibrium conditions.
So if it's Q, is that going to be the same time that the cell is measured?
Correct. Right, exactly. You'll see. We're going to solve. We're going to talk through one of these. So guys, let's put this in context really quickly, and then we're going to fiddle around with all of this. So I don't think you need to write this down. You'll be doing this in a minute, but let's fiddle with this equation really quickly. So guys, what is E cell? The voltage of the battery at any point in time. But guys, when we think about different points in time, what is changing over time about the battery? Molarities. And that is what Q brings in. Because guys, Q is the concentration of products divided by the concentration of reactants, but because it's Q, this can be the concentrations at any time in the life of the battery. So what we do is we sort of take a snapshot and we say, here goes the battery, is doing its thing, stop. And we can say, what is the concentration of the products? What is the concentration of the reactants? Those are the, hey, how are you? Thank you. Let me get the door for you. Hi, guys. Thanks, guys. Oh. Okay, so guys, the idea is this. We go products divided by reactants. Remember, those are the concentrations of the ions in the two beakers. And we go, at these concentrations, what is the voltage of the cell? Do you get the idea? That's what this allows you to calculate. So Q represents the new concentrations. E cell is the voltage of the cell. So guys, what is that dependent upon? Well, first of all, what's this? The voltage of the cell where it started. What is the significance of this being negative? It's dying. It just goes down from there. So the idea is, and think through this with me, the voltage of the cell is equal to the voltage of the cell when it starts, cathode minus anode, minus what happens to the cell as the concentrations change, making the battery less effective. So guys, when then does the battery die? When this is equal to the voltage that the cell began with. Does that make sense? So that's what it looks like mathematically to say goes to equilibrium. It's not quite that simple because there's a factor here that includes the number of moles of electrons that are being tossed about. But guys, fundamentally the idea is this. When this factor on the right, which changes based upon the number of electrons and the concentration gradient changing, when this factor cancels out, when it becomes the same as the initial voltage of the cell, then the battery's dead. Does that make sense? Okay. So guys, with that said, let's apply this to our good friend zinc copper battery. I know, it should have been. So guys, scratch this down with me and then you've got a bunch of questions to answer. By the way, guys, that equation that you just wrote down is what is called the Nernst equation. So guys, notice what we've done. This is the reaction that takes place in the battery, right? In the left-hand cell, zinc is being oxidized to zinc ion. In the right-hand cell, copper 2 ion is being reduced to copper. This is just the net ionic equation for the battery that we know and love. Okay? Questions for you. Question 1. What is the Kc expression for this reaction? Write it down. You done? I'm going red. I'm done. Guys, what happened to the zinc and the copper metals? They're solids. They don't belong there. Is that okay? Now, guys, question number 2. How many moles of electrons are being exchanged in this process? How many moles of electrons are being exchanged, guys? 2. Zinc goes to zinc 2+, that's losing 2 electrons. Copper 2+ goes to copper, that's gaining 2 electrons. So we now know that N is equal to 2. Now, guys, we know this. The voltage of this battery is 1.10 volts. Where did this come from? Cathode minus anode. Now, guys, set up the Nernst equation. What does the Nernst equation look like for this process? Write it down. I'm going to put it up here. So I've got E cell is equal to, yeah, I'll put it there, is equal to 1.10 volts minus 0.0592 divided by 2 times the log. How'd I do? Okay. Is that right? Oh, good. I like it when I do things right. Okay, so now, guys, we need to start taking this idea of the Nernst equation and use it predictively, which kind of gets back to question 8 from the homework. So, guys, question is this. What change would cause the voltage of this battery to go up? And you may want to go back and look at your initial diagram for the battery. So guys, let me do that and we'll connect these two together. So if we go back here, guys, what are the things that we can change about this battery to change the voltage? There's only one thing we can change. Concentration. So we can either make the zinc ion more concentrated or we can make the copper ion more concentrated. Which of those two changes would make the voltage go up? Copper go up or zinc go up? Uh-oh, we are a nation divided. Yeah, you thinking through it? You guys okay? Copper up? Because guys, if you're not sure why, just think this. What does the battery do as it happens? Copper ion becomes copper metal. That means if there's more copper ion, it can happen more easily. So copper up. Okay, but now guys, what about this? What if you don't want to spend the time to draw the battery? Well, guys, look at this. Le Chatelier's principle, do you see it? Which direction is this battery spontaneous, left or right? Right. We write these as spontaneous processes. So guys, this is the spontaneous direction for the reaction. So if we want the reaction to go better, Le Chatelier's principle, do we add reactant or product? Reactant. Does that make sense? If you want the reaction to go this way, you want the amount of reactant to go up. Because if reactant goes up, that drives the equilibrium to the right. So which one of our ions is the reactant? Is copper ion the reactant or is zinc ion the reactant? Now you've got a second way to know how to make the voltage go up. You figured it out initially because you looked at your picture of the battery and you saw that copper is where reduction happens, so more copper ion, more of it to be reduced, better battery. But guys, if all you're given is the reaction, then all you got to do is look at this and go, if I want the battery to be better, and if the battery goes that way, then adding reactant, Le Chatelier's principle, will make the reaction shift right, better battery, and the reactant concentration is the copper ion. Does that also make sense? Now let's do it a third way. Look at the math. We have established that adding copper ion makes the voltage go up, right? Adding copper ion makes the voltage go up. How does that work mathematically? So copper goes up. How does the math work out? If copper goes up, what happens to the value of this? Becomes smaller. What happens to the log of that? Smaller. And multiplying that by this, which is now a constant essentially, because it's now divided by 2, which doesn't change. Guys, that means the bigger this gets, the smaller this gets, the smaller the log of it gets, the smaller this entire thing becomes, and because we're subtracting a smaller number, it has a smaller impact on voltage. But what about this? You ready for a big idea? What happens if this becomes bigger than zinc ion? So if copper is bigger than zinc ion, what does this fraction become? Smaller than 1. What is the log of a number smaller than 1? Negative. So now this becomes negative. And what happens if we subtract a negative number? We're adding it, and we can actually make the voltage go up. We can make the voltage bigger than 1.10 volts by making the concentration of copper ion greater than zinc ion. Does that make sense? Do you understand the idea? You've seen it relative to your diagrams, you've seen it relative to the balanced equation, and now you've seen it mathematically. Get the idea? Okay. So guys, another question then. What change would then cause the voltage to drop? The opposite, right? Increasing zinc. So guys, what about this? Shall we do the math? Before you do, though, read it. Let's predict and then let's calculate. What is the voltage of this cell if copper ion is 5 molar and zinc ion is 0.05 molar? Guys, don't touch your calculators yet. Let's think about this. You're going to be disappointed in the answer. So guys, look at what we did. Copper ion. So guys, copper ion, we just made 5.0 molar. And then zinc ion, we're making 0.05 molar. Now guys, let's do this qualitatively first. Will the voltage go up or down? Compared to 1.10 volts, will this be higher or lower? Higher, right? Because if copper's big and if zinc is small, that favors the battery, right? Now guys, look at our concentration gradient. How many times more concentrated is 5 than 0.05? Isn't it just 100? Guys, it's 100 times. 100 times more concentrated. Certainly, this is going to be a crazy good battery if we've got a concentration gradient of 100-fold, right? Do the math. Yeah, do the math. Do the math. Yeah. That's cool that you guys figured that out. That's not a coincidence. So guys, this number right here, when you take the log of it, it's 0.01, right? So guys, or I'm sorry, no, it's a, wait.
When you take the log of it.
So if you just do the division, it's 0.0.
Right, 0.01. And then the log of 0.01 is -2. And then the 2's cancel. And so functionally all you're doing is adding this. So guys, you get this crazy steep molarity gradient, and all that buys you is 0.06 of a volt. Wildly disappointing.
So, I mean, that means the inverse of that issue. So this
Right.
battery
Yes.
very slowly.
Yeah, because who said the battery dies when the molarity becomes 0? Somebody said that earlier, yeah, Brent. And I corrected you and I said no. But Jake is exactly right. The same logic that says huge concentration gradients favoring the battery don't buy you much voltage. Huge concentration gradients working against the function of the battery are caused by big concentration changes, but they result in small voltage changes. We could even do the math, right? What would that look like? How big would the concentration gradient have to be in order for the battery to be dead? What would that, I've never thought of it. What would that, wouldn't it be the inverse log of 1.10?
Now, you've got to have your other.
You're right. You've got to have the other factors. So I guess the thing that we're solving is 1.10 is equal to 0.0. I've never thought to do this. This is pretty cool. Well, here, I'm just going to make that into a, so 0.0592 divided by 2 is 0.030 log of functionally x. So 1.1 divided by 0.03, and then the inverse log of that.
No, because you subtract it, right? So it's a minus on the right. So
Whoa. I'm getting 4.6 times 10 to the 36th. Does that make sense? So the place where this battery dies is when this is equal to 1.10. And when that is equal to 1.10, this is functionally doing the division 0.030 in the log of x. So solving that for x, it's 1.1 divided by 0.03. And then the inverse log of that? Good night. So the concentration gradient is 4.6 times 10 to the 36th fold?
it's got to be 10 to the 36 times.
More concentrated, which is functionally 0.
Yeah.
So Brandon, we're going to go back and say yes. Functionally, it basically falls to 0. Go ahead. 0.0592 divided by 2. Hey, but guys, understand what we're doing right now is just interesting mental gymnastics. They're not going to ask you this on the test. But it is a fascinating question. What does the concentration gradient have to be to kill the battery?
So, your round is like 10.
Yeah, yeah.
If you leave it that small difference, it's like, it bumps up the 10 to 37.
Oh, really? Oh, so it's another order of magnitude. Interesting. So guys, that was fun, at least for me. Are you okay with the ideas? Because we're about to wrap up the day. No, I mean, there's an answer to it. It'd be 1.1592. Yeah.
So I know that if you want to double the population function at that infinitely more times copper ion.
Right, or pick different elements. Yeah. You guys okay? All right, guys, follow along. Don't write this down, but this is interesting. So we just, again, and it was completely freeform, talked about when these batteries will die. So now let's come back to that and again, don't write this down. Guys, let's come back to this idea of dying batteries. So here's what we know. Returning to this idea of a reaction quotient. So this Nernst equation actually doesn't just work for batteries. Guys, this Nernst equation can be used to actually study any redox reaction. But instead of reactants, you'll see instead of cathode and anode, we just make it generic and we say reduction and oxidation. So guys, this then is the idea. Answer these questions for me. I think you can. So guys, we are now going to talk not about batteries, but we are going to talk about generic chemical reactions, electrochemical reactions, redox reactions. But guys, the ideas are similar. So, when a reaction is at equilibrium, you can be thinking dead battery, or you can be thinking any other chemical reaction. Guys, when a reaction is at equilibrium, what's true of Q and K? They're the same, right? Because Q is K at non-equilibrium conditions, so if we're at equilibrium, Q and K are the same. Is that okay? Thought number two. What is the voltage of a cell when it's at equilibrium? 0. The battery is dead. Whether it's a battery or just a redox reaction, guys, at equilibrium, there is no voltage. Good? Now, guys, watch what we can do. We are going to take the Nernst equation and we are going to rewrite it for equilibrium. So, guys, let me remind you of the Nernst equation. It says E cell is equal to E naught cell minus 0.0592 divided by N. Got it. Divided by N. And then, guys, we've got the log of Q. So, guys, you ready? Let's replace. We'll do this in red. So now we are going to rewrite the Nernst equation at equilibrium. So what do we now know at equilibrium? Well, first of all, what's true of Q and K at equilibrium? They're the same, so let's replace this with a K. Now, guys, what else do we know about equilibrium? The battery's dead, so what's the voltage? 0. Is that the cell or is that E naught cell? That's this, so this is 0. That's a 0. So, guys, when we rewrite this then, look at what we get. We get this. Get it? Now, guys, at this point, what we can do is we can actually take this equation and solve it for the log of K. And when we solve this for K, you missed it. And okay, here we go. This is the animation I brought back. This used to be the end of the year. And when we solve it for K, this, the end of the year, is what we get. But guys, notice what this is telling us. There is a relationship between K, products divided by reactants, and the voltage for the cell. So if you know the standard voltage for a cell, you can figure out the value of Kc. Here's the problem. They took this equation away from us. Because, guys, this equation works for electrochemical cells. But they've decided that rather than give you this equation, which relates equilibrium to electrochemical cells to Kc, they want you to know this generically. So we need to bring in another idea. So guys, remember, we're talking about equilibrium, right? At equilibrium, we've established two things. At equilibrium, voltage is 0. At equilibrium, Q is K, right? Now let's bring in Gibbs free energy. At equilibrium, what is true of delta G, the change in Gibbs free energy? What is it? It's 0. Guys, we got to review. You ready? If you have a delta, remember delta G is equal to delta HT minus T delta S, right? If you have a delta G that's negative, what does that tell you about the reaction? Spontaneous. If you have a delta G that's positive, what does that tell you about the reaction? Spontaneous in the other direction. Or you could call that non-spontaneous. What do we know if delta G is 0? It's at equilibrium. And taking that idea, we end up with this. It turns out that if we pick 0.0592 apart and replace it with R and T, which is what those variables actually bring you to 0.0592, and then we undo this and rewrite it in reference to Gibbs free energy, rather than just talking about a relationship between K and voltages for electrochemical cells, we can make this generic for all reactions, and we find out that if delta G is 0, which is true at equilibrium, we can then figure out the value of K by simply knowing its temperature and the value of R. That is the equation that's on the AP test. Now we're done. Yeah. What?
If delta G is 0, we divide the negative RT.
But if it's not, but you can also apply it in other situations.
Delta G doesn't have to be 0.
Correct, exactly. Right. Yeah. Yeah, you're right. Keep going. Here, hey guys, so here's the deal. I was considering not even throwing this in. Frankly, it's a frustration to me because it's taking something meaningful in electrochem and replacing it. Just understand this is the equations on the equation sheet. I felt it at least necessary to introduce you to the idea, the thought being that there's also another way of coming up with K, not relative to voltages because they took that away, but coming up with K relative to Gibbs free energy changes. This isn't even going to be in the homework. Understand it's there if you get into the AP test and you find that you're given Gibbs free energy values and you got to solve for K, it's there. But guys, don't get too caught up in it. So
We can just use that for any situation.
if you've got the variables, yeah.
Okay.
Yep.
It doesn't have to be at equilibrium.
Correct.
They would say,
Right.
hey, you've got this, this, and this.
Right, but your question is intriguing. So guys, let's do this. Here's your homework. 61 through 65. Got it? You good? Okay, so 61 through 65.